In this problem, a uniform cylinder of radius r is rotated about its axis to the angular velocity omega naught and then placed into a corner. The coefficient of friction between the wall and the cylinder as well as the ground and the cylinder surface is given is mu. We're asked to find before the cylinder stops, how many turns does it make? This is really a nice problem. I think this problem not only tests your understanding of the basic kinematic equations, but also how well a student can really draw the free body diagram. All those skills are tested. Now, to let's say solve this problem, let us start from the question. Okay, so the question asks us how many turns will the cylinder accomplish before it stops? So that means this has to stop. Okay. Now, if it has to stop, the angular acceleration must be in the opposite direction of the angular velocity. So the angular velocity is in the counterclockwise sense. So the angular acceleration will be in the clockwise sense. Now, let us look at how to obtain this angular acceleration or the retardation which is going to stop the cylinder. If there is no friction, okay, so if there is no friction, I hope we understand that this is not really possible. Okay, so now why is that not possible? If I pretend that there is no friction, okay, so the surfaces are really smooth. If the surfaces are smooth, and if I look at the free body diagram, what forces are really acting on the cylinder? From the ground, we have this normal force. Acting in the upward direction. Okay, and the earth provides a gravitational force in the downward direction. So let's say the mass is not given, so maybe the student should guess that the answer should not really depend on the mass. Okay, so if I just take mass of the cylinder as m, I can say that the gravitational force is mg. Okay, the vertical wall provides a normal reaction to the right, so that is n. If there is no friction, if the surface is smooth, we have only these forces. Now, with these forces, can the angular acceleration be generated? If you look at them, mg obviously acts on the center of mass, so it cannot provide any torque. The normal force provided by the wall, the line of action of force passes through the center, and the normal force provided by the ground, the point of application of force, the line of action of force, we should say, that passes through the center. So none of these forces provide any torque, so you cannot get acceleration. So in a case where there is no friction, the cylinder must spin forever. Okay, so but since we have friction, so let us see how to get the angular acceleration. Okay, now this is sometimes confuses a student how to really get the correct direction of friction. That's important to understand. So now if I look at the let's say contact point near the ground, if there were no friction, okay, so always imagine a scenario where there is no friction. Okay, if there is no friction, the points that are touching the ground, okay, so these points which are touching the ground, they would nicely slide to the right. Okay, so you see these points, let's say whatever points that are going to touch the ground, they're going to slide. I think I should use a different color. Yeah, so these points that touch the ground, they slide nicely to the right. Because the surface is rough, the surface is going to apply a friction force preventing this motion. So we can say that the surface applies a force to the left. So let's call that as F1. And another thing to note here, the cylinder is clearly slipping. Okay, so at the corner, because it is slipping, the friction force that gets applied here is the maximum possible friction. Okay, so that's one thing that we need to understand. And we can do the same thing at the wall. Okay, so the points that are touching the wall, okay, so if there were no friction, okay, so these points would slide down. Okay, so they would want to slide down because there is friction and the wall is going to apply force in the upward direction. Okay, so let's call this as F2. And again, the same idea, the cylinder is going to slip. So this is again the maximum possible frictional force. Okay, so I think the free body diagram is complete. Okay, now see, when students are learning to sketch free body diagrams for the first time, this might take a while, but I think it is really important to understand that it's okay to take time, but if you think through the problem correctly and then finally you get the free body diagram, trust me, that's like it's like solving more than half of the problem. Because without a proper free body diagram, if you write down Newton's second law, and then even if you are very good at solving equations, it's like complete waste of time, right? I mean, you're not going to get the correct answer anyway. Okay, so I always suggest that a good free body diagram, what is a good free body diagram? It's a correct free body diagram, wherein you are showing all the relevant forces that you must show. Once you do that, I think the rest is like easy. Okay, so trust me on that. Okay, now here, how do we get the angular acceleration? So now let's apply Newton's second law for rotations. So about the center of the cylinder, or let's say the axis passing through the center of the cylinder, so about let's say axis of the cylinder, if I apply net torque is equal to I alpha. Okay, now we want to take a direction to be positive, so let's say the clockwise direction is positive. Okay, so the torque is provided by the friction forces. So if you apply the right hand thumb rule, okay, let's say the four fingers are pointing from C to the point of application of force, let's say from C to this point, and then if you curl them, okay, so the thumb actually points into the board. Okay, so if the thumb points into the board, the curling fingers show the direction in which the cylinder would get the angular acceleration. So here we say that each of these friction forces, okay, so I highly suggest that you use your right hand thumb rule for obtaining the torque. So we know torque is R cross F. So if I look at the angle between the position vector, which runs from C to the point of contact, okay, and the frictional force, that's 90. So magnitude wise, I can just write here RF sine 90, and the, let's say when you use right hand thumb rule, the thumb points into the board. Okay, it is suggesting that the angular acceleration is in the clockwise sense. Now both the forces, both the friction forces are providing torque in the same direction. So if I write down the torque, I will get F1 max into R plus F2 max into R, and this is I alpha. Now they're saying it is a uniform cylinder, so it is a solid cylinder. The moment of inertia will be mr square by 2 and then alpha. Okay, so now to get alpha, we need to find the friction forces. So how do we get the friction force? So I think let's look at how to get them. Now how to get these friction forces? If you look at F1 max, F1 max is mu times the normal force, which is mu n. Similarly, F2 max, the vertical friction force, that is mu times n2. Okay. Now see how this problem is progressing. Okay, so we wanted alpha, and then to get alpha we want friction forces, but now we don't know these normal forces on which the friction forces depend. But I think that should not be very difficult. So if you look at the vertical direction, okay, the cylinder does not have any acceleration. So vertically the cylinder is in equilibrium. Even horizontally the cylinder is in equilibrium. So we can say the net force is 0. Okay. So vertically 0, I think I'll write it here, horizontally also 0. The net force on the cylinder is 0. Now look at the vertical forces. In the downward direction I have only mg, and the upward direction I have the normal force n1 plus this F2 max. This is equal to mg. Now horizontally, the normal force provided by the wall balances the friction force provided by the ground. So we can say N2 is F1 max. Again, so if I write F1 max as mu times N1, I get a relation between N2 and N1. So now come back to this equation here. Okay, so N1, now what is F2 max? This is mu times N2. That is equal to mg. Now let us substitute N2 here. Again, this is like elaborate algebra, so you have to be careful. Okay, so mu times N1 is equal to, okay, so from here if you see, this is N1 into 1 plus mu square is equal to mg. So N1 comes out to be mg by 1 plus mu square. So once you get N1, so we have N2 is simply mu times this. So you have mu mg by 1 plus mu square. Okay. Now that we have N1 and N2, we have friction forces, right? So now if I go back to the first equation, okay, so let's transfer these normal values and friction values to that equation. So F1 max is mu times N1. Okay, so here this would be mu N1 is mg by 1 plus mu square into R. Again, please note that this should be plus sign because both the torques are in the same direction. Okay. Sometimes students make that mistake. And then F2 max is okay, mu times this. So I think here, so you already have mu, so this becomes a mu square. So note that this should become mu square mg by 1 plus mu square into R is equal to mr square by 2 alpha. Okay, so now what is alpha? I think we can eliminate R on either side. I think mass also can be eliminated. So if we look at it, what do we get? I think I can take mu mg. Oh, sorry, I said mass can be eliminated, right? So mu g by 1 plus mu square. I think that's a common factor. And then I have mu plus 1. And then a 2 also comes here. And then I divide by r. Okay, so that is the angular acceleration. Now, if I write down the kinematic equation for like simple rotation about an axis, this axis is like is anyway not moving, so it's like a fixed axis. So I'm sure we know this. Okay, the final angular velocity minus the initial angular velocity square is equal to 2 times alpha into the angular displacement. But they're asking how many turns does it really make before it stops. So if I take that it makes n turns, for every turn it covers a angular displacement of 2 pi radians. So we can substitute that here. Now if it is stopping, finally this is 0, and then initial angular velocity is omega naught square. Okay, here it doesn't matter whether I take it as positive or negative, so that anyway disappears. And then if I look at it, my sign convention is clockwise positive, so the displacement is in the negative direction. So that's important to take. Let's write down alpha. Let's transfer the huge term. Okay. So what do I have here? 2 into mu plus 1. Carefully transfer this. Okay, plus 1 by r into 1 plus mu. There is d r into 1 plus. I hope taken everything. Yeah, 2 into mu into g is there, mu plus 1. Okay, so alpha is done. And again, the angular displacement is negative here, so I'll use it with the negative sign. Number of turns, and then each turn actually makes it turn, let's say, by 2 pi radians. So that's the thing. So finally we get the number of turns that the cylinder makes before it stops would be, I think we can take everything. Okay, so in the numerator I'll have mu square plus 1 into r to omega square divided by, it will be, I think there will be 8 pi. Yeah, so it will be 8 pi mu into mu plus 1 into g. Okay, so those are the number of turns that the cylinder makes before it stops. Okay, so I hope you enjoyed this problem.